Let's look at another combustion example. In this example, we're going to have a furnace. Now, this furnace, is going to burn a fuel that is LPG, It's 250 moles of this. I'll call that my basis. And this has a composition of 65 mass percent C3H8, 25 mass percent C3H6, and 10 mass percent C4H10. Okay, thing to note, we need to use mole percent because we'll be doing reactions. So all those mass percents going to give us an opportunity to review for the exam. Now, in this particular case, all of the C3H6 and C4H10 are consumed, and 90% of the C3H8 is consumed. There is not any CO detected in the flue gas, so this is complete combustion. If the LPG is burned with 45% excess air, we want to find the ORSAT analysis of the flue gas and the molar ratio of steam to dry flue gas in the exit stream. So we're going to add to this some air that is 45% excess, and we're going to get out flue gas, but it's easier to think of this as dry flue gas and water. That just is going to kind of simplify the calculations a little bit. That way, the ORSAT analysis will be what we calculate. So, the first real complication here is that they gave us mass percent. So let's just refresh ourselves on how we convert from mass to mole fractions. So the first thing I need is I'm going to need the molecular mass of my various compounds. Those are available in the appendix. Again, you should start familiarizing yourself with that if you haven't already. We will be using it extensively for the remainder of the course. But for C3H8, the molecular mass is 44.09. For C3H6, it's 42.08. And for C4H10, it's 58.12. Okay, so the way we convert from mass to mole fractions, recall that the easiest thing to do is to assume a basis. So I'm going to assume that there is 100 grams, since I've got mass percent, of LPG in my system at this point. I'm going to be eliminating this very soon, so it doesn't need to match what I have for my total feed. So make a little table, and for each species, I've got C3H8, C3H6, and C4H10. I have the weight fraction for each of those is 0.65, 0.25, and 0.10. If I figure out the mass for each of these based on 100 grams, then I have 65 grams of C3H8, 25 of C3H6, and 10 of C4H10, giving me a total of 100 grams. Now I have the molecular mass data. Remember that the units on this, if I'm working in moles, which was my choice, these are units of grams per mole. This has units of grams. So to get to moles, I'm going to take the mass in grams and divide by the molecular mass. Okay, so 65 divided by 44.09 is 1.474. 25 divided by 42.08 is 0.594. And 10 divided by 58.12 is 0.172. Now, add up to find out how many moles I have. In this case, it's 2.240. Divide each of these by the total number of moles. This is NT, total number of moles, and that will give me the mole fraction. We'll call it YI. So 1.474 over 2.240 is 0.658. And continuing with this, I end up with those as my mole fractions. And it's always a good idea to just add at the end and make sure that they do in fact add up to 1. If you get 1-digit error in your last place here, that's probably fine. That's just a round off error. So now we have the mole composition of the feed. Okay? We know that there are 250 moles of this LPG. Okay? So therefore 250 moles of LPG is 0.658 moles of C3H8 per mole of LPG. And so therefore I have 164.48 moles of C3H8 in my feed. Similarly, I'm going to have 66.28 moles of C3H6 and 19.19 moles of C4H10. So next we need to develop the combustion reaction. So in this case, my combustion reactions, C3H8 requires 5 oxygens for complete combustion to 3 CO2 plus 4 H2O. C3H6 requires 4.5 oxygen to make 3 CO2 plus 3 H2O. And C4H10 requires 6.5 oxygens to make 4 CO2s plus 5 H2Os. So I can use this to come up with the theoretical O2 requirement. Okay, so I have 164.48 moles of C3H8. Okay, I require 5 moles of O2 per mole of C3H8. I have 66.28 moles of C3H6, and I require 4.5 moles of O2 per mole of C3H6, and I have 19.19 moles of C4H10, requiring 6.5 moles of O2 per mole of C4H10. Therefore, my grand total, I need 1,245.395 moles of O2. That's the theoretical required air. Now, theoretical air is based on the actual amount fed in the fuel, not the amount that actually reacts. Okay? Now, if I want to figure out how much actual air first of all, this is oxygen, so 1,245.395 moles O2. 1 mole of air is 0.21 moles of oxygen. So this tells me the theoretical air. And now then I have 45% excess, so multiply by 1.45, telling me that I need 8,600 moles of air. Okay, so that's how much air will be fed. Now I need to treat this, I need to do the multiple reaction game, okay? So I have fed in my various streams. I have C3H8, C3H6, C4H10, and I have O2 and N2. Out, I'm going to have all of those potentially, as well as CO2 and H2O. So potentially I have all of those. However, they did say that all of the C3H6 and C4H10 are consumed. So those are going to be completely consumed. So I get to do balances here. Now I can choose whether I want to do mole balances using extent of reaction with my 3 reactions, or I can choose to do atom balances. I find that atom balances tend to be safer here, simply because, oh dear, okay. The reason is if you accidentally messed up on your balancing of your chemical reaction, it will kind of erase any mistakes you made there. So I'm going to do atom balances. And this is input equals output for an atom balance. I don't have to keep track of reactions. I'm going to switch pen colors here for a little bit of clarity. So C, all right, I have 3 coming in with C3H8. Okay, and that was 164.48 moles. I have 3 that come in with C3H6, and that was 66.28 moles. I have 4 that comes in with C4H10, and that was 19.19 moles. Now, how much comes out? Well, I'm going to have the amount that comes out as CO2, and there's 1 carbon with each of those. Okay, and I have whatever is left of the C3H8. Okay, now they told me how much is going to come out of the C3H8. And this is times the feed, the flue gas flow rate. Okay, I'm going to rewrite that so that it's the number of moles of CO2 coming out. And this is going to be 3 times the amount of C3H8 that came out. But remember they said that 90% is consumed, so 10% C3H8 remains in the flue gas. So initially I had 164 moles. Now I'm going to have 10% of that. That's 16.448 moles that leave. All right, so that's my carbon balance, and I have one unknown here, the number of moles of CO2. And based on that, number of moles, okay, we're having a hard time with our writing. Number of moles of CO2 is going to be 720 moles of CO2 that exit. All right, now then if I do a balance on H, okay, I have 8 hydrogens that come in with this C3H8. I have 6 that come in with C3H6. I have 8 that come in with C4H10. And H leaves, well, okay, 8 leave with the C3H8, and then 2 leave with the water. And I find that 953 moles of water leave the system. Okay. How about oxygen? All right, so oxygen is going to only come in with the flue gas. So it's 21%. I'm having a hard time writing. Of the 8600. Okay, and then there's 2 atoms in each of those molecules. All right, when it leaves, it's going to be in the remaining O2. And there'll be 2 with each of those. It's going to leave with the CO2. And it's going to leave with the water. And based on this, the amount of O2 that leaves is going to be 643 moles of N2. Now, don't forget the nitrogen. This is the one that people tend to forget about. Nitrogen comes in and it leaves. So the amount that came in initially is going to be the amount that leaves. So 0.79 times 8600 is N of nitrogen, and in this case it's 6794 moles of N2. That was an O right there. All right, so I have a total, okay. In the flue gas, there's a total of 9,126 moles of wet gas. But if I ignore the water, there's 8,173 moles of dry gas. And I can then turn this into an ORSAT analysis by simply taking moles of CO2 per mole of dry gas. So 720 over 8173 means that I have 0.20% well, sorry, I did CO2 first and I'm writing down C3H8 first. So C3H8, 8.81% CO2, 7.87% O2, and 83.12% N2 is the ORSAT analysis of my final product.